White dwarfs represent one of the most common end states of stellar evolution and play crucial roles when paired with companion stars in binary systems. These dense stellar remnants, typically containing the mass of the Sun compressed into a volume similar to Earth, participate in a variety of astrophysical processes that shape our understanding of stellar evolution, accretion physics, and explosive phenomena. The interaction between white dwarfs and their companion stars in binary systems creates unique conditions that lead to some of the most energetic events in the universe, from novae to Type Ia supernovae, while also serving as laboratories for studying extreme physics. White dwarfs are compact stellar remnants formed when low to medium mass stars exhaust their nuclear fuel. These dense objects typically have masses between 0.2 and 1.4 solar masses, with the upper limit known as the Chandrasekhar limit. White dwarfs in binary systems often display distinctive characteristics, including surface temperatures ranging from 20,000 to 40,000 K, particularly in B white dwarf X-ray binary systems. The formation of a white dwarf represents the final evolutionary stage for the majority of stars in our universe, making them common components in binary star systems. When a white dwarf exists in a binary system, its intense gravitational field can significantly influence the companion star. In close binary systems, the white dwarf's gravity can distort the companion star, particularly when the companion fills its Roche lobe, the region within which material is gravitationally bound to the star. This gravitational interaction often leads to mass transfer from the companion to the white dwarf, creating an accretion process that powers various astrophysical phenomena. The nature of this mass transfer, whether stable or unstable, largely determines the subsequent evolution and observable characteristics of the binary system. Cataclysmic variable stars, CVs, represent one of the most well-studied classes of white dwarf binary systems. These systems consist of a white dwarf primary accreting hydrogen-rich material from a donor companion star. The defining characteristic of CVs is their irregular brightness variations, which can increase by large factors before returning to a quiescent state. The accretion process in CVs typically results in the formation of an accretion disk around the white dwarf, which emits strong UV and X-ray radiation due to the release of gravitational potential energy from the infalling material. The shortest currently observed orbital period in hydrogen-rich CV systems is approximately 51 minutes, indicating how compact these binary systems can become. Symbiotic binaries represent another important class of white dwarf binary systems, typically consisting of a white dwarf paired with a red giant companion. In these systems, the cool giant star loses material either through Roche lobe overflow or via a stellar wind, which then accretes onto the hot white dwarf, often through an accretion disk. Symbiotic binaries exhibit distinct variability patterns, transitioning between quiescent and active phases. During quiescence, the accretion, mass loss, and ionization processes reach an equilibrium, resulting in a relatively stable spectral energy distribution. When this equilibrium is disturbed, the system enters an active phase, characterized by significant changes in both the nature and rate of energy release. These systems are valuable for studying stellar evolution, stellar winds, ionized nebulae, and accretion processes due to their unique interstellar dynamics. B white dwarf X-ray binary systems, BEWDs, represent a rare type of X-ray binary where a white dwarf accretes matter from a rapidly rotating B star. These systems form through binary evolution in which mass transfer spins up the accretor to become a B star while the donor evolves into a white dwarf. BWDs can be identified by several distinctive features, including supersoft X-ray emission with temperatures around 0.1 keV, X-ray luminosities ranging from 10 bar 33 to 10 bar 38 ERG-US, and deep nitrogen, 0.67 keV, and oxygen, 0.87 keV, absorption edges in their X-ray spectra. The white dwarfs in these systems tend to be particularly massive, typically between 0.9 and 1.35 solar masses. Despite theoretical predictions suggesting BEWDs should be 7 times more common than B-neutron star systems, they remain relatively rare, with only 8 confirmed systems as of recent records. Double white dwarf systems, consisting of 2 white dwarf stars in a binary orbit, represent an important evolutionary endpoint for many binary star systems. These systems likely originate from more massive progenitor binaries that have undergone two phases of mass transfer or common envelope evolution. Population synthesis models indicate that approximately 30 to 40% of certain binary systems evolve into double white dwarf configurations. These systems are particularly significant as potential gravitational wave sources, detectable by instruments like the Laser Interferometer Space Antenna, LISA, with models suggesting they may constitute LISA's most likely gravitational wave source. Additionally, under certain conditions, the merger of two white dwarfs in these systems can lead to exotic objects like extreme helium stars, R Corona Borealis stars, or even type Ia supernovae. White dwarf-neutron star binaries represent a class of systems where a white dwarf orbits a neutron star. The stability of these systems significantly depends on the mass of the white dwarf component. Research indicates that only binaries containing helium white dwarfs with masses less than approximately 0.2 solar masses undergo stable mass transfer and evolve into ultra-compact X-ray binaries. Systems with higher mass white dwarfs typically experience unstable mass transfer, ultimately leading to tidal disruption of the white dwarf component. This instability arises from the efficient removal of angular momentum in mechanical disk winds that develop during super-Eddington mass transfer rates. The fate of these systems has important implications for understanding the observed populations of ultra-compact X-ray binaries, radiopulsars with white dwarf companions, and certain transient phenomena, like calcium-rich gap transients. Mass transfer in white dwarf binary systems occurs through several mechanisms depending on the binary configuration and evolutionary stage. In close binaries, when the companion star fills its Roche lobe, material flows through the inner Lagrangian point toward the white dwarf. Alternatively, in wider binaries with giant companions, the white dwarf may accrete material from the companion's stellar wind. The transferred material, particularly in cataclysmic variables, is typically rich in hydrogen and forms an accretion disk around the white dwarf due to conservation of angular momentum. The rate of mass transfer significantly influences the system's behavior and stability, with higher transfer rates generally leading to more energetic phenomena. When material is transferred from a companion to a white dwarf, it rarely falls directly onto the white dwarf's surface due to conservation of angular momentum. Instead, the transferred material forms an accretion disk around the white dwarf. These disks are regions of significant energy release, powered by the loss of gravitational potential energy as material spirals inward. The dynamics of accretion disks around white dwarfs involve complex processes, including viscous heating, radiative cooling, and potentially magnetic interactions if the white dwarf possesses a significant magnetic field. In many systems, instabilities in the accretion disk can lead to periodic brightness variations, as seen in Dwarf Novae outbursts, where the disk transitions between cool, dull states and hotter, brighter states. The stability of mass transfer in white dwarf binary systems critically affects their evolution and observable characteristics. Stable mass transfer occurs when the donor star can maintain thermal equilibrium as it loses mass, resulting in a sustained, controlled flow of material to the white dwarf. Conversely, unstable mass transfer occurs when the donor's radius expands faster than its Roche lobe as it loses mass, leading to runaway mass transfer and potentially catastrophic outcomes. The stability largely depends on the mass ratio of the binary components and the response of the donor star to mass loss. In white dwarf neutron star binaries, for instance, only systems with helium white dwarfs below approximately 0.2 solar masses undergo stable mass transfer, while higher mass systems experience instability leading to tidal disruption of the white dwarf. Classical novae represent one of the most common explosive phenomena associated with white dwarf binary systems. These events occur in systems where a white dwarf accretes hydrogen-rich material from a companion star. As this material accumulates on the white dwarf's surface, it creates a layer of hydrogen atop the carbon-oxygen core of the white dwarf. When the pressure and temperature at the base of this hydrogen layer become sufficiently high, runaway hydrogen fusion ignites, rapidly converting hydrogen to helium. This thermonuclear runaway causes a dramatic increase in luminosity and the ejection of the accumulated hydrogen layer from the white dwarf's surface. Importantly, only the surface material is expelled during a nova explosion. The white dwarf itself remains intact, and continues accreting material, potentially leading to recurrent nova events over time. This cycle of accretion, explosion, and renewed accretion represents a fundamental process in white dwarf binary evolution. Dwarf novae constitute a subclass of cataclysmic variables characterized by semi-regular outbursts of smaller amplitude than classical novae. These phenomena result from instabilities in the accretion disk surrounding the white dwarf. During quiescence, material accumulates in the cooler outer regions of the disk. Once a critical density is reached, a thermal instability propagates through the disk, causing it to transition from a cool, dim state to a hot, bright state. This transition results in a significant increase in the system's brightness before the disk eventually cools and returns to quiescence. Dwarf novae outbursts typically recur on timescales ranging from days to decades, with the specific recurrence time dependent on the mass transfer rate and disk characteristics of the individual system. Type Ia supernovae represent the most energetic and destructive phenomena associated with white dwarf binary systems. These catastrophic explosions occur when a white dwarf approaches or exceeds the Chandrasekhar mass limit of approximately 1.4 solar masses. Two principal scenarios have been proposed for type Ia supernova progenitors. The single degenerate scenario, where a white dwarf accretes material from a non-degenerate companion until reaching the critical mass, and the double degenerate scenario, involving the merger of two white dwarfs. In either case, when the white dwarf reaches sufficient density, runaway carbon fusion ignites in its core, leading to a thermonuclear explosion that completely destroys the white dwarf. Recent evidence, including the discovery of supra-Chandrasekhar mass supernovae and delay time distribution measurements, increasingly favors the white dwarf merger model for many type Ia supernovae. These events are particularly significant in astronomy as standardizable candles for measuring cosmic distances. White dwarfs in binary systems exhibit distinctive spectroscopic features that aid in their identification and characterization. These features vary depending on the type of binary system and the nature of the ongoing mass transfer. In symbiotic binaries, for instance, the spectrum typically shows both the absorption features of the cool giant companion and emission lines from the hot ionized gas surrounding the white dwarf. B-white dwarf X-ray binaries display characteristic deep nitrogen and oxygen absorption edges in their X-ray spectra. The accretion disks in cataclysmic variables often produce strong emission lines, particularly of hydrogen and helium, while the underlying white dwarf may contribute broad absorption features. During outbursts or active phases, the spectroscopic features can change dramatically, providing valuable information about the physical processes occurring within these systems. Photometric variability represents one of the most distinctive observational characteristics of white dwarf binary systems. Cataclysmic variables, by definition, exhibit irregular increases in brightness by large factors before returning to quiescence. Symbiotic binaries display transitions between quiescent and active phases, with significant changes in luminosity during active periods. The variability patterns and timescales differ markedly between different types of systems. Dwarf novae show recurring outbursts on timescales of days to years. Classical novae exhibit dramatic, unpredictable brightness increases. And symbiotic novae display extremely slow outbursts that can remain near maximum brightness for years. The prototype symbiotic variable star Z Andromedae exhibits irregular variations up to about 4 magnitudes in amplitude, exemplifying the complex variability patterns these systems can display. These photometric variations provide astronomers with crucial information about the underlying physical processes and system parameters. Many white dwarf binary systems are significant sources of X-ray and ultraviolet radiation, with the specific emission characteristics providing valuable diagnostic information about the system's nature and ongoing processes. In accreting systems, the infouling material releases gravitational potential energy, often in the form of X-ray and UV radiation from the accretion disk or the boundary layer, where the disk meets the white dwarf surface. B-white dwarf X-ray binaries exhibit distinctive super-soft X-ray emission with temperatures around 0.1 keV and luminosities ranging from 10^33 to 10^38 ERGS. Detection of these emissions can be challenging in some systems, as the white dwarf is often embedded within surrounding material that absorbs much of the extreme UV and soft X-ray photons. The intensity and spectral characteristics of these high-energy emissions provide crucial information about the mass transfer rate, accretion efficiency, and white dwarf properties. White dwarf binary systems serve as critical laboratories for testing and refining models of stellar evolution. These systems preserve a record of their evolutionary history through their current configurations, component masses, orbital periods, and chemical compositions. For example, the existence and properties of BEWD systems provide constraints on theories of binary evolution, particularly the conditions under which mass transfer can spin up an accretor to become a B star while allowing the donor to evolve into a white dwarf. Studies of the population of symbiotic binaries in the Magellanic Clouds help constrain the number and distribution of these systems, which has implications for our understanding of type Ia supernova progenitors. By comparing observed populations of different types of white dwarf binaries with theoretical predictions from population synthesis models, astronomers can refine their understanding of the complex processes governing binary star evolution. The diverse array of white dwarf binary systems provides unique opportunities to study accretion physics across a wide range of conditions. From the stable, wind-fed accretion in symbiotic binaries to the disk instabilities in Dwarf Novae, these systems exhibit various accretion regimes that test theoretical models. The transition between different accretion states in response to changing mass transfer rates offers insights into the physics of disk instabilities, boundary layers, and magnetic interactions. White dwarf binaries also allow for the study of accretion at different timescales, from the rapid dynamics of dwarf nova outbursts to the secular evolution of type Ia supernova progenitors. The detailed observations of these systems, combined with hydrodynamic simulations of mass transfer and accretion processes, continue to advance our understanding of the complex physics governing matter transfer in compact binary systems. White dwarf binary systems host some of the most extreme physical conditions in the universe, providing windows into physics under extraordinary circumstances. The thermonuclear reactions that power classical novae occur under conditions of temperature and density that cannot be replicated in terrestrial laboratories, making these systems essential for understanding nuclear processes in extreme environments. The merger of white dwarfs in double degenerate systems involves complex hydrodynamic processes, potentially including detonations and deflagrations, that challenge our computational capabilities and physical understanding. The accretion disks in these systems operate under conditions of temperature, density, and radiation pressure that span many orders of magnitude, testing our theories of plasma physics and radiative transfer. By studying these extreme conditions, astronomers gain insights not only into astrophysical processes, but also into fundamental physics that may have applications beyond astronomy. Close white dwarf binary systems represent important sources of gravitational waves, particularly for space-based gravitational wave detectors. As two white dwarfs orbit each other in a tight binary, they lose energy through gravitational radiation, causing their orbit to decay and their orbital period to decrease. This process accelerates as the separation decreases, potentially leading to a merger. The gravitational wave emission from these systems is typically in the millihertz frequency range, making them ideal targets for planned space-based gravitational wave observatories. The amplitude of the gravitational wave signal depends on the masses of the white dwarfs, their separation, and the distance to the binary system. Double white dwarf systems with short orbital periods are expected to be among the strongest and most numerous gravitational wave sources in our galaxy for instruments sensitive to this frequency range. The Laser Interferometer Space Antenna, LISA, a planned space-based gravitational wave observatory, is expected to detect thousands of white dwarf binaries throughout our galaxy. Population synthesis models suggest that double white dwarf systems may constitute the most likely gravitational wave source for LISA. These detections will provide unprecedented information about the population of close white dwarf binaries, including their mass distribution, orbital period distribution, and spatial distribution throughout the galaxy. By measuring the gravitational wave signals from these systems, astronomers will be able to determine their physical parameters with high precision, even for binaries that are electromagnetically faint or obscured by dust. This will dramatically improve our understanding of the formation and evolution of these systems, with implications for models of binary star evolution and the type Ia supernova rate. White dwarfs in binary systems play fundamental roles across astrophysics, from powering some of the most energetic phenomena in the universe to serving as laboratories for extreme physics. The diverse array of binary configurations, cataclysmic variables, symbiotic binaries, double white dwarf systems, white dwarf-neutron star binaries, and B-white dwarf X-ray binaries. Each provides unique insights into stellar evolution, accretion processes, and explosive phenomena. The mass transfer dynamics in these systems, whether stable or unstable, determine their observable characteristics and evolutionary pathways, potentially leading to novae, dwarf novae, or even type Ia supernovae. The observational signatures of white dwarf binary systems, including distinctive spectroscopic features, complex photometric variability patterns, and characteristic X-ray and UV emissions, allow astronomers to identify and classify these systems, while also providing crucial information about their physical properties and ongoing processes. As astrophysical laboratories, these systems enable tests of stellar evolution models, investigations of accretion physics across diverse regimes, and studies of extreme physical conditions that cannot be replicated on Earth. Furthermore, close white dwarf binaries represent important sources of gravitational waves, with future missions like LISA expected to detect thousands of these systems, providing new insights into their population statistics and evolutionary histories. The continued study of white dwarfs in binary systems remains vital for advancing our understanding of stellar evolution, accretion physics, explosive nucleosynthesis, and gravitational wave astronomy. As observational capabilities improve and theoretical models become more sophisticated, these cosmic laboratories will continue to yield new discoveries and deepen our understanding of the universe's most extreme stellar systems.